Hello everyone, and welcome back. The differential equation we're going to take a look at today is very similar to the last one that we solved. Although now, instead of just gravity being the only force acting on our falling object, we're now taking into account air resistance, or the drag force. And the drag force is equal to the drag force coefficient, which is just a constant coefficient based on the geometry or material that the object's made of, times velocity. So the force of drag actually increases as the object is accelerated downward and its velocity increases. So we have a relationship, a direct relationship between two terms in the equation this time, between a function and its derivative. So let's get started. I'm not going to go through Newton's second law again. We already know how that works, and I've already made the substitution of dv dt in for acceleration. So let's just solve this equation. The first thing I'm going to do is divide both sides by this entire term mg minus bv. And I'm also going to divide both sides by m. So we'll have 1 over m is equal to 1 over mg minus bv times dv dt. And now we're going to recognize that the dv and the dt are quantities again, and we're going to multiply both sides by dt. So we'll have 1 over m dt is equal to dv over mg minus bv. So that's what we have just separated our variables. We have all the t's on this side and all the v's on this side, so now we can integrate both sides in terms of time on the left and in terms of velocity on the right. And once again, at the start of the object's motion, t is equal to 0. And we're integrating from 0 to some time. And velocity, we're going to assume that we're dropping the object again, so its initial velocity is 0, and we're going to integrate to some velocity v. Now the integral is a little bit more complicated in this case, so I'm not going to go over the integration steps, but I'll tell you that it can easily be done with a u substitution if you know how to do that. So I'm going to bring this over here and integrate the left side. That's just t over m. And integrating the right side, negative 1 over b times the natural log of mg minus bv, evaluated from 0 to v. Okay? I'm going to multiply both sides by negative b. So we'll have minus bt over m is equal to the natural log, and now I'm going to evaluate my bounds. I'm going to plug them in. So our top bound is v, so we'll have for the first term the natural log of mg minus bv, and for the second term v is 0, so we'll just have the natural log of mg. And one of the laws of logarithms states that if you have a log minus another log, that is equal to the log of the first thing inside divided by the second thing that's inside. So minus bt over m on this side, and that will all be equal to the natural log of mg minus bv over mg. Okay. And now we can exponentiate both sides because we want to solve for v. Remember, that's over here inside the natural log. We want to raise everything to the e. So we have e to the minus bt over m is equal to mg minus bv over mg. Now I'm going to multiply both sides by mg, and we'll have mg minus bv. So we'll have mg over here, and then is equal to mg minus bv. I'm going to subtract an mg over here, and we'll have a minus bv. And you can check my algebra on this, but we should end up with bv is equal to mg minus mg e to the minus bt over m. Okay, and now factoring out an mg from this expression and dividing both sides by b, we will get our velocity as a function of time, which is equal to mg over b times 1 minus e to the minus bt over m.